So I think if you're in this session, you pretty much know that DynamoDB is a managed NoSQL database. It's highly available. It's replicated on multiple availability zones. The main reason why a lot of people are using it is because it's very, very simple to set up. If you ever created a DynamoDB table, you know what I'm talking about. It's just a couple of clicks. And if not, I really encourage you to do it. Dynamo has a pretty generous free tier, so you can test DynamoDB for almost nothing. But the second reason why people are using DynamoDB is for this. If the blue line represents the number of requests that you have on your table, if you do things correctly, and today we're going to be talking about doing the things correctly, you're going to see a latency that is always completely flat, like the green line. So in DynamoDB, you can have reads under 5 milliseconds and writes under 10 milliseconds. Regardless the number of incoming requests you're going to have, if you follow the best practices that we're going to talk about today. Now, everything that I'm going to talk about is in the DynamoDB documentation. So there's no secret. Everything is online. The thing is, the DynamoDB documentation is 700 pages. So I don't expect anyone to read the whole thing. So I'm going to try to condense this in just 40 or 50 minutes, right? So first, let's start with the definitions. The tables, the APIs, the data types, and so on. So this one is a bit of a misnomer, but DynamoDB has a concept of a table. But if you know about relational databases, the tables on Dynamo are a bit different because inside a table you have items, and items have a flexible amount of attributes, right? You don't have to follow, like in a relational database, you don't have to follow a schema and everyone should all the items should have the same attributes. No, items can have different attributes. The only thing that you have to specify when you create a table on Dynamo is the hash key. So the hash key, as the name implies, allows you to find an item, and you can augment this hash key with the range key, which is optional, but we're going to see now what you can do with it. That is going to help you do more refined searches and more complex queries inside your tables. So regarding the data types, you have fairly classic data types like strings, numbers, binaries that you can also augment with sets. So sets of strings, of numbers, of binary data. And DynamoDB is not only a key value store, it's also a document database. So you can store complete JSON structures inside a DynamoDB table. Each item, in that case, would be limited to 400 kilobytes. And you have like specific types on top of it. So if you know about JSON, you will notice that, in fact, DynamoDB supports a superset of JSON, because JSON by itself cannot have like binary data, but I showed you here in this previous slide that you can have binary sets, and you can even have those binary sets inside your JSON document. For example, you could, let's say, like put like an image inside a document. I definitely don't recommend you to do this. You should use Amazon S3 for that, but perhaps you want to encrypt some information inside your DynamoDB tables, and for that you can embed it as a binary data. Okay, so now the hash. So it's important to understand that the hash not only uniquely identifies an item, but it can identify a set of items. So you have a hash. So we compute the different hash space. And those different items are going to be distributed in the hash space. And then we're going to partition the hash space. So this is how we are going to be able to scale the table with multiple partitions, right? And each partition is replicated in 3 different availability zones. Okay, so even if we lose like a complete availability zone, you still have access to your tables. Okay? Now, we're going to add the range. So in order to, as you saw, the hash somehow randomizes the distribution of the items. Now, if you want to get an order in a query that is retrieving you multiple items, you could use, for example, a range that is going to allow you to sort the different items on your request, right? So a hash and range key together, they form a way to uniquely identify one item, because you can have, for example, a hash that has multiple items, and then the range will restrict this. We're going to see the examples now. Okay, but here, perhaps, if this is still a bit blurry in your mind, we're going to see that in more details. Just keep in mind that the hashes are distributed across multiple partitions. Okay, now let's add indexes on top of this. So if there's only one thing you have to understand in DynamoDB is what we're going to talk about now. Because the main reason why people are using databases like DynamoDB or MongoDB or Cassandra or any kind of other NoSQL database is because they want to scale, they want to sustain a high number of reads, writes, they want to be flexible and not have a schema. But now when they are porting applications that have been built for relational database, and when they are moving to a NoSQL database like Dynamo, often the way you manage the indexes is what's going to make the whole difference in the performance of your application. Or this is also what can make or break your application case regarding on how you want to use a NoSQL database. So Dynamo has two types of indexes. One is the local secondary indexes. So imagine that you have this table, right? So with different attributes, and one attribute is the hash, the second one is the range. So those two form the key that allow you to uniquely identify an item, right? Now, you can create a local secondary index by keeping the same hash, but choosing another range. So here you see that I'm going to choose the attribute A3 as another range. I'm keeping the same hash. That's why also we call it a local secondary index. And then I can project the other attributes. So the local secondary indexes are great in order to create other indexes to give you a richer set of queries. But keep in mind that you are limited to 10 gigabytes per hash key, which in most of the cases is hugely sufficient, but in others might be perhaps something you want to look for. Then there's the global secondary indexes. So again, I'm going to clarify this, but the idea here is that when you create another global secondary index, you can specify another hash key that is different than the one from the table. So pretty much a global secondary index is almost exactly as if you had like a copy of the existing table with another hash attribute. Now, if it's a copy of the other table, we have to transfer the data because we can project the attributes, right? And the way it works is like this. So your client writes to a table, and then you get the response, but at the same time, behind the scenes, asynchronously, we're going to project the attributes and the data that the client changed. So now you see that another main difference between local secondary indexes and global ones. So by default, I recommend you to use the global secondary indexes because you can create them at any time. They are way more flexible. They are not limited with the 10 gigabyte hash set key limit. But they are going to be eventually consistent because as you saw here, we're going to send the response and asynchronously update the global secondary indexes. So if this scenario of eventual consistency in the secondary index is okay for you, I will definitely recommend you by default to use the global secondary indexes instead of the local secondary. Okay, just let's finish the theory part with the scaling, because this is also a source of misunderstandings with DynamoDB, which is DynamoDB is an amazing database, but like all the tools, you can use them effectively, and you can use them in a very inefficient ways. So, as I explained earlier, Dynamo scales by partitioning the tables, right? So, and when you provision a table, perhaps you already saw that basically you have two buttons to adjust the provisioning of the table. You provision how much read capacity you need and how much write capacity you need. So you see here, so the read capacity units, WCUs, they are measured in 1 kilobyte writes per second, and reads is 4 times the same capacity. So a read capacity unit is how many blocks of 4 kilobytes you can read per second. Okay, so RCUs by default, the read capacity units, they are consistent. But if you are okay to do inconsistent reads, you can have 8 kilobytes capacity per second for one RC unit. Now, let's do some math, and I promise it's the last time that I do theory or this kind of stuff in the session. This is one of the important things to understand on how DynamoDB works internally. It's the number of partitions that DynamoDB is going to create and automatically maintain on your table. So we compute it in two ways. So we're going to keep the number of partitions for throughput. So basically, we take the amount of read capacity that you provision for reads, divided by 3,000, and the same for the write capacity divided by 1,000. Everything is in the documentation, right? I don't remember the page, perhaps 320 something, but it's in the documentation. The point here is that you see that this equation tells you how much DynamoDB node or DynamoDB shard can sustain. One shard of DynamoDB can sustain 3,000 read capacity units, 1,000 writes, or we limit the size of the shard to 10 gigabytes. Because you see, either we shard in terms of throughput, or we shard in terms of size. That is, the number of partitions you can have on one table is the total size of the table divided by 10 gigabytes, because we don't want to have more than 10 gigabytes in one DynamoDB shard, right? So, and then, for example, a computation is this. You take the maximum of both. So let's say that I have a table here, you see at the top, that has 8 gigabytes of data. I'm provisioning 5,000 read capacity units, writes only 500. So the number of partitions for throughput, I see it's 3. The number of partitions for size, like 8 gigabytes can fit in one single partition, so it's 1. Okay, so I take the maximum. So this table in this scenario is going to be sharded in 3 nodes. And then the nodes are going to be also like replicated on multiple availability zones, but you're going to have 3 partitions. Okay? Now, a quote from the documentation. The way you're going to be able to get all the throughput of DynamoDB is by having uniform workloads. So the question is, how uniform is uniform, right? So there's different ways to mess that up. The first way to mess it up is to, for example, have all the queries that go in one of the shards, like here. You see the color goes red the more a shard is hot, and the more requests it got. So here, for example, I definitely have a non-uniform workload. All the queries are going to one shard. And here, I have another way to have a non-uniform workload. This one is on time. So during a couple of periods, I have some bursts of requests, like let's say, I don't know, roughly every 5 hours, I have huge bursts of requests that always go in different shards. Now, Dynamo has a built-in burst mechanism. That is, you can accumulate burst capacity for something like 5 minutes of the amount of capacity units you provision. So you see here, you always have 5 minutes of capacity. If I provision 1,200 read capacity units, I can burst over my limit. So Dynamo is not throttling you as soon as you go above, right? It has some built-in mechanism. Now, if you consume all the 5 minutes, you're going to be throttled down to your maximum capacity unit. So what happens in your code when you have throttle requests? So for example, if you're using Java or Python and so on, you're going to have exceptions. So you have in your code, you have to be able to be resilient and to catch those write or read requests that go above the throttling capacity. And now we're going to talk about how to avoid this. So what causes throttling? So throttling is, of course, once is what we just saw. If you provision, like let's say 1,000 reads, 1,000 read capacity units, and you're reading way more than that, so you're going to be throttled, obviously. Now, the other one is when you have non-uniform workloads, and those are perhaps a bit trickier to detect. So let's see the scenarios, and we're going to discuss about everything here now, so to make sure that we understand all that. Couple of scenarios. So the first one, event logging. So we just talked about Kinesis. It's a very classic use case to take all the data of Kinesis and to dump it into a DynamoDB table for time series. And you end up with non-uniform workloads. Why? Because most of the time, the information that you want is the information of the last couple of days or the last couple of weeks. But if you put all the data in the same table, you're going to have some partitions that are never going to be requested because it's data that is from the last month and no one cares about this data anymore. So that's why here the best practice would be to have, like, depending on your workload, obviously, different tables. It's very easy to create tables on DynamoDB. You're not limited. It can be done with API calls, depending on the proximity of the data in time. So here it's, for example, tables per month. And you can see that the different tables have a different capacity unit provisioned on it. So you limit the sharding yourself, and you are kind of creating, like, at the application level, a sharding mechanism based on the tables. So you can here get all the throughput, especially for the events that are the closest to the event now. Now, another scenario, just to talk about the request. Let's say that we have like an image sharing application where people can tag each other, like the way, for example, you will do it on Facebook. So you have a couple of queries to do. All the images for the user, you can sort those images by dates, the images of whose user has been in some of the tags, and so on. So the way we're going to build this is we're going to create one table, pretty simple, with the hash key is going to be the name of the user, and then the range key is going to be the ID of the image. And then we're going to have other attributes like the dates, the link into S3 of the image, and so on. So the hash, remember, is only equality queries. So you can only get like all the items that exactly match this hash. And now the range, you can do like negations, superior, inferior, and so on. So the way I'm going to get all the images from a specific user is pretty straightforward. Is you do a query only on the hash key. Give me all the items where the hash is the name of the user. And that's it. You're going to have them. Now, you want to sort that by date. So we have a problem here because those two are the hash and the range attribute. We don't have any index on the date, right? So you saw what we do. We are going to create a local secondary index. So the way it's going to be implemented is like this. So this happens behind the scenes. Basically, I keep the same hash, which is the user. And then I choose another range key, which here is going to be the date. And then the request is, again, pretty straightforward. Get me all the images of this user by decrementing date. And I'm still on an index. So it runs extremely fast. Now let's see about the tags. So I'm going to create another table, which is going to be like the relationship table. So in a specific image ID, what are all the users that are appearing in this image? So I'm tagging the name of the user. So here again, it's hash and range. And for example, if I want to have the list of all the users that appear in one specific image, so I give the name of the image, and I have the list of the users. Okay, so that's pretty straightforward. And if I want to tag another user, I just insert a new line in the table. Now, if I want to query all the images where a specific user is, again, I can't do it with this table because the hash is here. This is just the range, right? So if I want all the images where Alice appears, I need basically to flip that out. So here I'm going to use a global secondary index because I need to specify another hash, not this. This is not a good hash for me, but this will be a good hash. So this is the difference between the local secondary index and the global secondary. So here I'm declaring global secondary index. I'm using these user attributes, and Dynamo is going to project the rest of the data. So I have like an alternate table, and then I can do the request as simple as it is. So from the global secondary index, get me all the lines where the user is Alice, and here I am. Okay, so that was to illustrate the difference between secondary indexes, local secondary indexes, and global secondary indexes. Now, let's look at another case for a game application. So let's say that we're doing like a mobile application of the tic-tac-toe game, And in fact, this is an example that has been implemented, so you can find it on the documentation, easy to deploy on Elastic Beanstalk. And the table looks like this. So now I represented the table in JSON format, something that is also supported by DynamoDB. And well, it works like this. So Alice starts playing. So you have in the table the position of her move, and the name of the next user is who's gonna play. So now it's Bob's turn. So he moves like this, and at this point, if Bob is smart, he realizes that by playing there, he's gonna lose, right? Because I mean, no need to be a machine learning expert or like to do a deep recursion tree. That is, if Alice plays well, she's gonna win in all cases. So what do you do in this situation? So you cheat, right? So he's going to cheat, and he's going to send multiple queries to the Dynamo. So all the queries are going to be processed at the same time because Dynamo is built for that. And the data is going to be inserted directly in parallel. And he's going to win in this situation. So you want to avoid that, obviously. So we're going to use a feature called conditional writes. So this is not something that is specific to Dynamo. The database systems that are used in most of the banks and in the credit card transaction systems use exactly the same kind of feature, which is based on item versioning. So the idea is you want to avoid concurrent updates on different data sets, right? So if two different people at the same time are adding money into my bank account, the way it's going to work from a program perspective is first the program is going to read how much I have on my bank account, let's say 1,000 shekels, and it's going to add 10. But the other program is going to read it at the same time. So they are both going to read 1,000, add the amount, and then update the database. So the database is going to process the two queries, one after the other, but they should be sequential, like one add, and then I get the result, and I add the other. So here's the same situation. So the way it's going to work is this. So the two requests are going to come concurrently. One of them are going to take the version number. So version number is Bob. So the second one comes like almost the same millisecond. So they take exactly the same data. But now the difference is in how you're going to update the data itself. So on your application, you're going to write the move, and you're going to update the version counter. And now you're going to update the database with the condition. So the condition is update the data if currently the data is in version 1. And the data is at the version 1 currently because no one changed it. But when the second request comes exactly with the same thing, put the item if the version is 1, so the request is going to fail because now I move to version 2. And even if DynamoDB is a distributed database across multiple availability zones, we guarantee this locking mechanism. So you can use this. In Java, there's a library that is supported with the Java tag. So by assigning the tag DynamoDB version attribute, you can have this done behind the scenes without you having to worry about maintaining the numbers and so on. It works in a similar way also on Python and Ruby, and we're porting this feature also to the other languages. Okay, so the conditional writes, this is important when you want to maintain like some kind of a locking state in a situation where you can have multiple concurrent transactions going into the same table. Now let's look at another scenario just to illustrate the point that I mentioned earlier about the different sharding and the partitioning system of Dynamo. So let's say that you're running Black Friday, and you're doing like a special sales, or for example, the same situation where you have like the World Cup and you're selling the soccer game tickets only during like a couple of hours. So you're going to have a huge amount of traffic into your website in a small amount of time. So I saw many situations where, well, the database administrator is going to connect to the AWS account, is going to provision more capacity units because, I mean, you read the documentation, right? So you see that if you compute the number of partitions that you're going to have, so let's say that here I have 2, I add more read capacity units, and it's going to create more partitions. Now, the thing you have to keep in mind is that, yes, it's going to create more partitions, but each partition receives an equal amount of read or write capacity units. So if you if you provision 100,000 read capacity units, it means that each of your shards are going to have like a specific amount of it, right? You're not going to be able to do like 100,000 reads on one shard. You're going to be able to do only 2,000 on one shard. And so now you see the problem. Let's say that you have like two very popular products on your database and they are in the shards, so you receive a huge amount of requests, but some of your very popular items are in a specific shard and this shard gets hot, and that's when Dynamo is going to start throttling you. And this is kind of a nasty problem, because you can say that, well, I don't know what's happening, right? I provision 100,000 write capacity units, but I don't seem to be able to go above 4 or 2,000, right? Because all the requests are going into this one and this one gets burned. So obviously, the first thing to do is look at the traffic on your application, see if you have like patterns of keys that are always requested more than the others. And in this situation, well, I mean, you use the same recipes that you're using probably already today. That is, you put a cache inside of DynamoDB. It's not because DynamoDB is a completely SSD-backed database that scales to like a huge amount of size that DynamoDB doesn't need a cache. In this situation, when you can have like hot partitions or items that are going to be read many times because of its popularity, a cache is definitely going to help you, not only from a cost perspective, because at the end you're going to be hitting the cache more often than you're going to be hitting DynamoDB, but also from a performance perspective, you're not going to burn all your read capacity units. Okay, so for the cache, you can use Redis. They are here. So you can use also Elastic Cache. You can use whatever caching mechanism you need. There's multiple libraries, regardless of the language you're going to be using. Okay, so cache is going to protect you against reads on hot partitions. But now let's see the reverse situation. Let's see the situation where you have a voting application, and now you need to write data. So let's say that you have this very popular TV show where you can vote for singers, and it's the final, and you have like 2 candidates, right? And your mobile application should allow anyone here in Israel to vote for one of the 2 candidates. So again, like from a developer perspective, the query is pretty straightforward, right? You update the vote on the candidate, and you do an atomic increment, because the way we see it previously with the different versions, DynamoDB supports atomic increments, even if it's a massively distributed database. So again, you will add one additional vote like this. Now the problem is when the day of the election comes. So if you again scale with adding 200,000 write capacity units, you're going to have the same problem as before. Right? Each partition is going to be able to sustain only a limited amount of writes. But the problem is you're creating hot partitions because you have only 2 candidates. So there's only 2 candidates, even if you provision the maximum amount of capacity that you can have on DynamoDB tables. One partition is going to have 1 candidate, another one the other. All the other partitions are going to be completely useless, right? And you're not going to be able to sustain the load. So how do you do in this situation? So for those of you who've been in operating relational databases, I want you to open your mind to other ways to do it, or to other ways of thinking. Because what I'm going to show now, a lot of people will argue that it's extremely dirty, but it's extremely efficient. And this is how, for example, Amazon scales during Black Friday. This is also how Shazam scales. This is how Spotify also sustains the similar specific loads. So here we go. You create multiple fake candidates, and you distribute them on multiple shards. And this is extremely effective because, I don't know, like if what happened in the UK is you have something like 10 million potential users coming into your application in just 30 minutes. You can prepare your table for the votes a couple of hours before. So you can create, as you see, like candidate A or candidate B. So you create like, I don't know, like 500,000 of them. And they are going to be distributed on all the different shards of your database. Now, from an application perspective, pretty straightforward. You almost don't have to change anything, assuming that your randomization function is can distribute the spread around all the different shards. So you just update randomly one of the candidates, and you add one vote. So your query is going to go to one of the candidates. Now, you're going to have another process that is going to periodically query all the candidates A, do the sum, and update the master candidate here with the total count. Now, the beauty of this mechanism somehow is that in one side, here you're writing on multiple different shards. So you're consuming write capacity units, but it's spread in a homogeneous way. And in the other hand, you are here consuming read capacity units. Okay, so you're reading on the different shards, so it doesn't burn your write capacity units, and you're only updating one of them that is not touched by the other part of the application. So this is an extremely effective technique that in some situations is perhaps perceived as not as academic, but it can help you to scale like to, I mean, I've seen an application that will be able to sustain, like the case of Shazam, something like 400,000 writes per second during more than 2 hours. Okay, let's see another case, a multiplayer application. So we take again the tic-tac-toe example, and let's say that we are in this situation where we have a leaderboard with multiple players. And here each player can be invited to a different game. So you see here the pending invitations. So I'm invited by one player, and I can accept or reject the invitation, and I can see the other results, right? So the table can look like something like this. I have the IDs of the game, the date when the game has been created, who is the host, who is the opponent, and what's the current status of the game. So again, my hash key is going to be only on the game ID. And the way it is going to work from the transition perspective is first the game has been created, it's pending, then the 2 players start, so it goes in progress, and once the game is finished, it's done. So the first query I need to do is what are the pending invitations for this user? Okay, so we already saw the trick. We just have to create a secondary index. It's pretty straightforward. So here I'm going to choose the opponent, and for the status, I'm going to have the range key. And the request is going to look like this. So I take all the details of the game for one player. So I'm the opponent. What are the games where I've been invited? I choose the one with a status pending. Now, let's say that I want to order those games by date because perhaps someone invited me on a game like this, like last year, and I never answer because I don't like the guy, right? So I only want to see the most recent games. So I should do something like ordering by date, right? Now there's a problem because I have a third criteria. The first one is going to be the hash, the second the range, but the third is what? So there's different approaches to this. And keep in mind that the way you pay on DynamoDB is by read capacity units and write capacity units. So you want to use those the least amount of time so you can be more effective from a cost perspective. So the first approach is to use a filter. So you're going to do your requests on the opponent and the date, and then you use, basically the filtering features of the querying language of DynamoDB in order to do the ordering and the filtering. But it looks like this. It looks like, let's say that you want to find all those orange dots in the bowl. So the query is going to take many of the blue ones, and the filtering is going to remove them after. Now, from a cost perspective, this is not efficient because it means that DynamoDB is going to read many of the items that you don't care about, but it needs to read them in order to be able to filter them or not, okay? Because the index is not complete. Now what I want to do, ideally if I have an index or if I'm sorted, I'm reading the minimum amount of information in order to keep the ones that are interesting for me. So the first way to do it is to use a filter. In some situations, if you don't need like a huge amount of throughput, or if it's the way you order your table is quite okay, you are not taking a lot of bad results, this could work. Another way is to use a composite key. So for the same people as last time, open your mind to other approaches. You can use a composite key. So from a development perspective, this is seen as, okay, let me retake this. From a theoretical perspective, it's seen as a bad practice. And it is somehow, because basically what you're doing is you're duplicating information in your table, right? So what I'm doing here from a code perspective is I'm just taking two attributes. I do the concatenation in the code of my application, and I create a third attribute. And then I use this third attribute in order to be my range key. So it's a bit dirty, but it's extremely efficient because now I have a query that goes on a hash and range. I don't even need to filter. So the result goes directly to the amount of information that I need. But I need to do this kind of dirty concatenation in my code, right? But extremely effective, something that is used in Pinterest and Instagram as well. Okay, let's see another example now. I just have a couple left. The classic application of a URL shortener. Let's say that for whatever reason you want to implement something like a bit.ly for your own application, right? So we all know how it works. You have a very long link that you want to send as a message. So you have a shortened link with an ID, and from an architecture perspective, when the client is gonna do the query, is gonna send you an HTTP GET request with the shortened link. The application goes to DynamoDB to see what is the version of what is the complete long link, and is going to redirect the client to this value. So the table can be very straightforward. The hash can be the short URL, and another attribute can be the long URL, and then you can have additional information about who created it at that time, and so on. Now let's say that we want to be a bit fancier. We want to do statistics. We want to see how many times a link has been accessed. So we can do that with, let's say, for example, a JSON document. So this is the kind of JSON item that you can have inside of DynamoDB. So you see that some attributes, some are directly attributes on the table, and here you have like nested values and so on. So the different data types that I show at the beginning definitely apply here. So you can have not only nested attributes, but you can also have nested maps of attributes inside a document. And the whole size, as I mentioned at the beginning, is limited to 400 kilobytes, which should be enough for most of the applications. If you need more than 400 kilobytes, you should really consider putting most of the data into S3 and only keeping the relevant information for the queries only into Dynamo. Okay, so let's see how it works. So this is JavaScript example code, but the structure is exactly the same in other languages. So if I want to add a new link, you see that there's nothing really magic. My request just contains the JSON object. I paste it like this, specifying the name of the table, and it works. Right? I only have to specify the hash key. Now, I want to do a resolution, so again, pretty easy. I just give the hash key that I want to extract. I can specify if I want a consistent read or not, and you see the results. So the answer is going to be the complete JSON document. Again, nothing magic here. Now I can be a bit fancier. I can do SQL-like expressions, and I can go into the structure of my tree in order to, for example, do like this, see all the most popular short URLs, right? So, and I can go, as you can see here, inside the structure of the JSON document to do my query. And the same if I want to get usage statistics, so I can update when the latest user got the link and the number of users who got this link. So the same things that we saw for the classic queries with incremental attributes and so on, you can also definitely do it in JSON documents. Okay, so quick recap on this. Amazon DynamoDB is not only a key value store. It was it in something like 2 years ago, but at that time we added the JSON document functionality. So even with everything that I mentioned earlier, also applies with the JSON documents with nested tree structures. Now let's see another example with this. Let's say that we have a messaging application, right? And well, the message is a complete JSON document with the metadata, the sender, pretty much like an email, right? So a way to implement it could be like this: a table where you have the recipient name, the date where the message has been sent, so this is the range key, and then who's the sender, and the body of the message in JSON will be in the message attribute. So this is pretty easy to get all the messages from a specific user and even sort them by date, because it's just a query on my hash and range key. Now the problem is that this is very ineffective. It's ineffective from a cost perspective. Because again, keep in mind that the way we charge you when you use Dynamo is how many read capacity units you're consuming and how many write capacity units you're consuming. So here, let's say that each item has something like 256 kilobytes. It's like long text of messages that you send from one user to another. So basically, you have to multiply 256 kilobytes per number of items that you are getting. So if you are retrieving 50 of those, so it's going to be 256 kilobytes times 50 items, and you're going to probably burn all your read capacity unit for that second already. So how do you do it? Well, pretty obvious at that stage. You split it into two tables. So one is going to have the metadata, another one is going to have only the body of the messages, and you can split it like this, right? So one table has only the attributes that you need to do the queries, and the other one is going to have like the message ID and then the complete body of the message into JSON. So from a cost perspective here, it's definitely way more effective. You only do a query here, and the data that you use here, the attributes, is something like 128 bytes for this situation, so pretty shorter, so you can have like a complete list of the 50 items. And if you look at it, it's pretty much the same way that most of the, like for example, the email clients work. First you see all the list of emails in your inbox, and then if you click on an email, then you go to the message itself and you do the heavy query. So it allows you to distribute the load on different tables. Now, the problem of this approach is, from a developer perspective, you're going to have to write twice. First, you write the metadata of the message in one table, and then you're going to have to write the body of the message in one table. And this is bad, right? Because we know that, well, as Ian mentioned just before me, things can fail. Everything fails all the time. So, well, you can have one write that's going to succeed, but the other is going to fail for whatever reason, right? So how do you solve this? Especially keeping in mind that NoSQL databases like Dynamo can't support distributed transactions the same way SQL databases will work because of the way they are distributed on multiple data centers, and because of the cap theorem itself, right? You're trading off consistency or throughput with you're trading off distribution with the consistency of your data set. Now, well, we have a solution on Dynamo, so it's using the global secondary indexes that we saw at the beginning. So I'm going to write only on the messages table, right? And then I'm going to project the attributes on the global secondary inbox table. And this way, from a code perspective, I only need to write once, and I leave to Dynamo the work of distributing the data to other tables. So yes, as I mentioned at the beginning, the writes are going to be eventually consistent. So if I'm in a situation where I'm doing a lot of read after writes, it may be tricky. But for this kind of applications where usually the way the user sees his messages first the list and then click to specific items is going to work definitely. And you can project the data for many other tables, like for example doing an outbox table or like even other folders. So just to wrap up on this, keep in mind that local secondary indexes and global secondary indexes are not only good in order to make your queries more efficient, but they're also good to help you minimize the amount of times you're going to write into Dynamo and to keep and replicate data for your application. Okay, so those were small situations that came from what we saw from different customers. The point for me was to illustrate the boring theoretical stuff that I explained at the beginning. I just have 3 minutes left, so I wanted to mention a couple of additional features that we couldn't cover. So obviously DynamoDB streams, but also features that are somehow interesting, like import-export. You can dump a complete DynamoDB table into Amazon S3 into another region, for example. Or it will allow you, for example, to copy a DynamoDB table and to reuse it for analysis or for a development environment. You can also have like auto-scaling for DynamoDB. There's a couple of interesting projects that allow you to implement this. We are also working on a feature that is similar to this. So if this is something that okay, how can I put this? If this is something that you will need, but you can wait for a couple of weeks, this is something that you will have on Dynamo out of the box. If this is something that you absolutely need right now, there's a couple of projects that you can find on GitHub that allow you to automatically adapt the number of read or write capacity units you have on a DynamoDB table by looking at your CloudWatch metrics. So otherwise, you can do it the kind of pager or old school way. On the AWS mobile application, you can have from your mobile phone access to the capacity units that you have on your DynamoDB tables. So if you still have a pager, somehow I pity you, but you can still get your mobile phone and add capacity units on the table. Regarding capacity units, keep in mind that you can also do cost optimization. The same way you have like reserved EC2 instances, you can have reserved capacity for DynamoDB table when you know that there's a minimum fixed amount of read capacity units or write capacity units that you're going to need. And if you never use Dynamo, or if you're a developer using Dynamo, this is something that is a bit hidden in the developer documentation. There's a version of DynamoDB that can run locally on your machine. So obviously, it's not going to scale at the same amount that DynamoDB can scale itself, but it's exactly the same API. So if you install it locally, it's a Java application, so it's just a jar to execute. The database is implemented with SQLite, but the front end of this database mimics the DynamoDB endpoints. So you can install this locally, develop while you are not connected, and then move your code into production in AWS, and it works exactly the same. Now, if you didn't use DynamoDB before, I recommend you also to give it a try, because it comes with a web shell in JavaScript that has a nice tutorial that does a walkthrough and explains you how to create indexes, how to do queries, and so on. So definitely give it a try. And there's also in the DynamoDB page a lot of videos and documentations that show all the different cases that I explained today, perhaps in an even more nicer way. So with that, thank you so much for your attention. If you have more questions, thank you. If you have more questions on Dynamo, I mean, you can come to the AWS booth, and pretty much everyone in the team will be able to help you on this. Thank you.